Alright, so let's continue with stack language. And honestly, I was thinking of renaming the language because it's a bit, too generic. So if you have any suggestions, let me know. It would be quite interesting to see suggestions for, the name of the language. And something else is that I managed to finish the type checking for the conditionals. I was like, oh, let me just try and see what I can change. And one thing led to another, and yeah, I finished them off screen, so I can show you what happened there, like what I did. It was like really repetitive, so I thought it's gonna be boring. So yeah, I have basically this. Let me zoom in a bit. Um, Stack context, right? And then we call stack context type check, right, on our AST. And the idea is we first have to define all the data types, right? And for defining data types, I just add the data type name to a list. And then we do the constructor and the field getters, right? So I also did these ones, which were quite simple. We just had to define the constructor. The constructor is a function, so we have the name of the data type as the name of the function, obviously, and then we put as the arguments the field types. You can see it here, and the return type of the constructor is also the data type name, and then we add the function. So that's how we define the constructor. It's pretty self-explanatory. I would say yeah, I haven't really checked. I mean, I checked only here if it's redefined, right? So if you redefine the constructor, somehow it's gonna show an error, right? So that's one of the errors that we can get in type checking, right? If you redefine the constructor, you're gonna get an error, right? Let's see the field getters now. And the field getters, I did the same approach here with generating the name by using the data type name dot field name, which in my opinion it's pretty nice, I would say. And then we have again the check if is redefined, and then the function name is gonna be this thing, like the field name, and the input type is the data type and output type is the field type. So that's how field getter looks like, right? That's how we are used to it. So that's how we define all the data types. Functions stayed the same, if I remember correctly. So nothing changed in defining functions. We just add the name, and it just looks like the AST. So that's how we define the functions. You cannot have overloads or overwriting other functions. So if you redefine a function, it's GG. Doesn't work. And then we iterate again the functions, and we type check the function bodies, right? And if the function is external, it means that we promise that the function works, basically. So ideally you would have as few external functions as possible then. And I mean, I kind of do. I only try to implement things in the language itself once I can do that, but sometimes you really need like functions like dupe, like rotate or swap. Those cannot really be implemented in the language itself. So, and yeah, type checking the function body stayed kind of the same, right? So we wait, I'm not sure I remember. Oh yeah, so here we have a stack, right? So how do we type check in this language, right? So we have a stack, and the stack is empty when we start the execution of a function. So let's imagine that the function that we are gonna type check is this function f that gets in a, b, and an integer for some reason, right? And it's supposed to return B or something like that, right? So how do we type check? Let's say we also call f in here. So maybe we do something like true hello 0 f string dot out and 0. So I mean this one works, right? But we start to type check this function. Well, we put on the stack a, b, and int, right? So we initialize the stack with the arguments. So it's like we assume that when f is called somewhere in the code, we are going to provide the right arguments. We assume that, right? So that's the first step. Then we run type check on the list of expressions, and at the end, after the type check is done, we check that the stack that we pass here as reference is gonna be equal to the function returns. So we check that the stack that we get at the end. So let's imagine that here we do something. We check that this thing at the end is equal to this, or I guess equivalent. We'll see if we need to do something else, but I'm pretty sure it's gonna be just checking if they're equal. So that's what I'm doing. I'm just checking if the stack is exactly equal to the return type. All right, so that's the idea. And in check expressions, we check each expression individually. And then if we have a number, we just add a number to the stack, right? We just add int. So if you put something like 0, the stack becomes ab int int, right? That's what happens. Then boolean, string, similarly, because these are special constructors, right, for our data types. For example, memory has a function constructor, which because you cannot really have like a memory, how do you call it, memory literal, it doesn't make sense, like a pointer literal, right? It's not that obvious. Maybe it's like, I don't know, the word null or parentheses, but I'm just gonna keep it simple and say that only integer, boolean, and strings have special constructs, right? And then we type check expression name, which is what we were doing last time. So type checking expression name is basically function calls, right? And what we are doing is check if the function is defined. So we defined all the functions, so it's impossible to have undefined functions, right? So we check that we have the function. So if I'm going here and I don't know, I say, okay, let's do the plus 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 operator or whatever that does, and I try to run main. Oh, I'm a X develop. I try to run main on examples 04. Is gonna say, well, this function is not defined. What are you doing? Right, so that's what happens there. And then we have type inference, which takes in the stack the current arguments and it generates an argument mapping. So if we execute stuff like rotate, which rotate has type definition like ABC, and it returns BCA, right? It brings forward the A. So it has this type. So we would have to literally figure out that A is this B is this int, and C is this int, right? So that's what we need in this mapping, so that we can say, okay, then the output is gonna be int B, right? So the stack after rotate is gonna be A int B, right? That makes sense. right? But maybe I can do something like, I don't know, swap, just to not do anything. So swap is like AB, but I mean, let's say the function returns A. So so it works, right? So we run rotate. So we have ABC turns to BCA. So that means that this A is this B is this int, and so on. So that's what type inference will do. So if we execute now the type checking, I think it's gonna be easier to see, right? So we expected an A, but we got A int B. So exactly what I typed here, right? So it figures out which types you have, and it's basically just doing a for loop over the arguments. Then we check if the first argument, for example, is actual data type. If it's not an actual data type, then we look in the mapping if we already mapped that argument, because you can have stuff like, I don't know, function that takes in. So it's like, you know, all these types need to match with this. So in this case, if I run it like this, I think, oh, it doesn't make sense because rot is an actual function that works. So if I define a function g that takes in 3 integers and somehow returns or like 3 things and returns a single thing, then you can see that these are not equal. So it should error here, I think, hopefully. Oh, forgot. I need to say it's extra, so we assume it's true, right? So function g has non-matching args. It expected AAA, but got that, right? And if we push another integer on the stack, it's fine, right? But it fails on the next function. Anyway, so let's delete that. Right, so it looks in the mapping. If it already has that type, then it needs to check if the types are the same, right? Because, you know, we cannot have two different A types. They have to be the same. And if you don't have that mapping, then we just create it. And then another case is if the type from the stack is not an actual type. Here I said I returned it for 1. Don't really remember. Right, but this is more like if you have an A on the stack. So if you have like this B here, and then you call plus, and the plus has the definition of int, right? You cannot, and it returns an int. You cannot, like, int matches with int, but this B doesn't match with this int. So that's impossible, right? You cannot take a generic type and match it to an actual type. So that's something. And the last case is both types are you know, actual types, so we have to check if they are equal, which is the simplest case. Anyway, that's type inference. Probably there is more to it, but that's what I was able to accomplish right now. Like, it's not Haskell level inference, but it's something. Yes, I hope. Hopefully it's gonna be fine. I mean, it works for rule 110, so I'm pretty happy about it. Right, and then the last thing we have to do in checking a function call is to remove. So if type inference worked, right? So if the inputs to the function are good, like this rotate, what we are supposed to do is to pop all the things from the stack. So you can imagine that, okay, we have rot. So what we are gonna do is remove all the items from the stack. So these things, and we go item by item in the return, and we use the mapping to decide what we put on the stack. So for example, we said that we mapped this A to a B, this B to an int, and this C to an int, right? So we have this mapping currently. We have A is type B, B is type int, and C is type int. So what do we have to put on the stack? We have to put a B, so that B is an int. We have to put a C, so that C is an int, and we have to put an A, which is a B. So that's how we build the new stack after a function call, right? So that's what the stack looks like after rotate. So it's exactly the manual process that we were following, right, in the beginning. So yeah, that's the function calls. And the last one is conditionals, and conditionals are similar because branches, you know, branches are branches. So yeah, first of all, we have to make sure that the first item from the stack is a boolean when you have an if statement. So if I do if we just do not do anything, it's gonna complain that we got a B, but we expected boolean, right? And after that, if we have a boolean, we pop it. So we don't really care if it's true or false at this stage, a type checker stage. We only care about the type. So that's really important to realize that you know, we just remove the boolean. We know it's there, it's fine. It can be only true or false. You cannot have other value for the boolean, so that's fine. It's 0 or 1. So let's remove it and continue with type checking. We make a copy for the stack, which we are gonna call the if branch and the else branch. So I mean, I call them like left hand side and right hand side stacks, but at this point we are gonna have two execution branches, let's say, right? So we can imagine a function that, like, let's say, I don't know, it's gonna be external, something weird, that takes in something and gives us a boolean, right? And it's gonna be external just to make sure that it works. Or I guess it's gonna be pop true, right? So it is what it is. If we call this weird function here, we can do the same inference as we did for rotate, and we realize that this A matches with this B. So the stack is gonna look like A int, we remove the B, and we add the boolean because the boolean is a type. Right? And then if we call if, we have a branch where we can do like plus, and a branch where we can do, I don't know, like 1 plus, for example, right? And this, why do we have two stacks here? Is because the first branch is gonna have some execution, and the second branch is gonna have a different execution. So we have to match both. And the idea is we type check expressions the same way we did for function bodies, for ifs and for the else's, and then we have to check that the if branch is equal to the else branch, otherwise we show an error. So we have this constraint that if statements must return the same thing, even though we can make it work with the if not returning the same thing, and you know, in the end you would still have the same result, but I think it's gonna be easier if we force this, because if we are gonna force the if else to have the same output, and it's like the same output type, then I think it's gonna make things a bit more easier, right? So that's what we do here. We force the if and the else to have the same result, and then if they are the same, we copy that result into the original stack. So since they're the same, because otherwise how do we know which branch do we choose for our main stack? We cannot really say. So yeah, if we run this one, it's gonna complain that the stack is mismatching, right? So we have int, and here we have two integers, right? I'm not sure why it also shows the a, because the a's are the same, but yeah, maybe I put something like I plus 1 or something. Anyway, so yeah, I guess the stack is mismatched here, right? We have int, and on the other branch we have int. So why is that? Well, here we do a plus, so this I guess after the if, the boolean is removed, right? So that's known. You saw we popped here the boolean. So plus is a function that takes into integers like int and generates a single int, right? So you can imagine that this is gonna be a int because it compresses these two integers, but on this side we have a int because we add an extra int, then we compress the last two integers into one, so we get this thing. Let me just repeat it. Right, so the branches are different. So let's say we do minus here, and now we have the same result for the if, right? We have a and integer, right? So next we can do something like pop, and pop is a function that, you know, it takes a and doesn't return anything. So a is gonna match with int, so we are gonna have a left on the stack, and a is gonna match with this a right here. So if we type check, it passes everything, and let's also just run it, and it also says hello. So it also, like, you can see that it inferred correctly all of the types from here. It went from the original stack to what it should output, right? And then we assume again that f is correct, so we come into this main function and we do the same thing for the main, right? And now we proved before that f is correct, so we can just use f in here, right? And it works as expected. It does the type inference, it does all of the things it should do. So yeah, that's basically it for the type checking. All right, so type check function, and that's type check. And I think that's it was like pretty interesting to get. Now the thing that, you know, it also works for, and I caught an error here. I guess it was just a typo. I had int in all of these, but this one should be empty. So yeah, and funny enough, the rule 110 code had no errors, which is pretty cool. So 03 rule 110, it doesn't have any errors. I guess something that I had to change to make that work though was that this function memory, right now it works only on integers, right? And I want to make it generic like this. But if I do this, then it's gonna complain that it got this AAA, but it was expecting int, right? So it got a generic type, but it was expecting integer. So the next logical step for me would be to make this memory like somehow parameterized like this. But it's going to be interesting, like memory allocate. How do you know which type it is? That's going to be interesting, because I guess for memory add it makes sense. It's going to be whatever type it in first, and even for memory store it's going to be quite obvious, but memory allocate is going to be kind of interesting. And yeah, the other thing we need to do is like allow these extra arguments here. So yeah, we'll see how we can do that, because I'm not sure if I want to do it right now or even today, but having this extra type on data types might be useful. So we can even have things like let's not add it there, let's do it like here. Even having the data type for tuples, or like tuple a b, so this one has even more types, and it's like a first, b second, right? So this is the data type, and we can even go to option a. Well, this one doesn't really work, because you would have to say a value so at this point we even go to different constructors, like somehow having to define types differently, right? We even get to having to define types in some other way, but yeah, the generic types should be a thing. Because yeah, we need like here you can even have a list of strings if you really want to, so you shouldn't be forced to say int, right? So that would be everything for type checking. I guess we are done for now. Obviously, once we add that generic types, it's gonna be again a bit of work in type checking. But I feel like for now I'm pretty happy with the current type checker. It allows us to do quite a few things. So okay, so the next step is let's try to add Linux syscalls to our language, because it's gonna make things a bit more easy, let's say, to read and write, and even do networking or other stuff as well. My only thing right now is if I should, like, how do people usually make it so that you don't have to implement manually each syscall, right? Like that's a pretty good point, because there are quite a lot, right? And it's not that great to implement each one manually. So if you remember from cool, we implemented each one manually, but we only did a few, the ones that we needed for reading and writing, opening files, closing, and like networking. So that's what we implemented. But in this case, I'd like to have, but I'm not sure how it's gonna work, right? Because if you have syscall, let's say 3, it has 3 arguments, right? So what are those arguments? And was usually the return is an integer, but like you can come here and provide this thing anything, but well, it should also be the syscall number, right? So maybe it's gonna be like this, or maybe something else we can do, but that's not really gonna work with memory. Like obviously it works, but it won't work with type checking. Is saying here we have some kind of memory with you know, the arguments, and then you can have syscall like this, and then this is the number, and then from the memory based on the syscall number we know what to expect here. But I'm pretty sure this one should be easier. Syscall 1 2 3 and so on. So for example, let's say we want to do, let's say we want to do the right syscall, because right is gonna be the easiest. This one is interesting. It's a const void buffer. I thought it's a const sharp, you know, but it's void, which makes it kind of interesting. Anyway, let's say we implement this syscall 3, and we have to make it in our main.c file. So let's go to assembler emit, and we emit the keywords. And so we do this part right here, and let me just add here function syscall 3, syscall 3. So it's gonna be syscall 3. That's what we called it, right? Yeah, sure, this one doesn't work on Windows. Suck it, install a real operator. I'm just kidding. And let's see. So here we have memory deref. Let's do syscall 3. What? Okay, so let's try to implement a syscall call. Right. So I'm probably gonna assume that you are using the right tools. So for example, we are probably gonna have function sys.read, or I guess right, syswrite. Syswrite is gonna be like integer. I want it to be it should be like memory and count in, and it's gonna do syscall 3. Oh, but see, like, how do we pass this thing? And it's gonna return integer. Because we need to also pass the syscall number. So maybe syscall number needs to come at the end. So we can just say, which syscall is this? Syscall 1, right? So this is how syscall write looks like. It's like file descriptor, the buffer that's shown, okay, in write, and then the count. But a nicer function would be like string.write, right? And this one, let's say it still takes the file descriptor and the string, but when it calls to this thingy, it should do something like dupe. So we duplicate the string on the stack. So we have int string string. Then we have something like I want to say a function string dot memory or something like string to memory. That's what I want. I want a function. It's probably going to be an external function that gives me a pointer to the string. All right, and we can still say it's gonna be memory int because it's like a void pointer, so it works to be memory int. Right, I would really like this function. So this one would convert this thing into memory like this. Obviously it's memory char, but we don't have that yet. So we assume that it's just memory int so that our type checking works. And then I can swap and string.length. Right, and this gives me int memory int. So now we can say sys dot write. So I think this would be the string dot write. Okay, and then string dot out could be defined like in terms of this function, but we need this string dot memory function. Right. Okay, so let's go back to our main thing, and let's say this is a syscall 3. So basically syscall 3 is just gonna call, so what we are gonna need some local variables, obviously. Basically here we need to pop, we need to take the int value. So we know that the stack in here, it has these 4 values, a, b, c, int, right? A, b, c, and int. So to be able to call the syscall, we need to pop the first thing from the stack, which is the syscall number. and let's store it on in the first variable in t0. So we pop, we dereference the int, and then we store it. Okay, what's next? I'm curious how memory is gonna work, because yeah, let's see if it's gonna work, honestly, because it's gonna be interesting. But I think we need to do the same thing again. So this is C, and we store it in T1. And let's also do T2 is equal to B, right? And now we can pop again. We can pop again, right? And this one is gonna be C, so, or I guess A, so the first argument or syscall. So let's say we move RDI RAX, so this is the first argument. Sure, I could even say, okay, let's allocate 32 and allocate 4 variables, and let's make it look the same. So T3 is equal to A, right? So we pop again. So now we should say here syscall 3, T0, T3, T2, and T1. So this is the syscall and these are the arguments, right? So what we have to do is put into RAX T0. Do I have a quick example? Yeah. So we put into RAX T0. Then we need to put into RDI T3. RSI is T2 and RDX is T1. And then we do just syscall. So I think that's how you do a syscall. With 3 arguments, like this one is the biggest one, right? And hopefully this memory thing is gonna be fine. But again, we need this memory string.memory function. So let's see if we can actually implement something like that. String.memory. So it's interesting. String.memory, it's kind of like the accessor for the string pointer itself, right? So that's how I see it. It's the same thing as len, but we do want to get the memory. So let's see if we can actually have something like this. String.memory. So where do we have string stuff? String substring, string concat, and string length. Let's say we copy string length because string length is string length. Right, and let's create string memory. right? So what do we need here is to pop, right? We have to pop from the stack, and then we need to move into RDI. Kind of this thing. The address of Rx plus 8, and then this one was a good point. We need to push on the stack, right? We need to push on the stack. So we cannot really call memory allocate or anything like that. I would say it should be just stack push. So we pop from the stack, we take this wait, I fucked the length one. Okay, anyway, let's leave it. Right, so here, for example, to store the length, we were just taking array_x and we were just pushing a new integer. But I'd say that for memory, that's even weird. Why do I do that? Because if you think about it, that's not really needed. Let's scroll down to emit data. So here we just do this kind of stuff. So string memory would just be stack pop v2, then rx move that, rdi, and then push, right? So it's exactly this. Oh, but see, here it's interesting. Here it's actually moving. I mean, I can keep it the same just to show that it's the same thing, right? So that's how you actually have to do this pop from the stack and then push. So that's how length should have worked as well, but here it's just like that, right? But let's see if it string right. Something is wrong with string right. std string right. It returns something, some error. Right. If we go to 01 hello, okay, let's modify this one, and let's say we do string.len show string.out 0. Is it gonna work? Fuck. No. So then how does Ah, I remember. Oh shit. It's because, yeah. So here, string length is not an integer, is the int value, right? And even the string wouldn't really work. We have to layer, right? So let's say I call here string right, string dot right, and stdout is 1, right? Stdout is 1. At least it type checks, right? At least it type checks. So like at arrayx plus 8 is the beginning of the string, so we take the address of that and we push that address on the stack. So this thing dupes string.memory swap. Maybe it's, you know, something inside of the thingy. Let's see. So next instruction, start. So basically 0 for type check. Here we push the number, here we push the string, and now we call string right. So let's go here, string right. So this one calls dup, this one calls string memory. I guess string memory shouldn't be that interesting. Right. So let's examine 64x from our heap. Right, so this is our heap basically. So we have something here, we have something else, and what's on the stack? Couldn't really say. Like after this string memory call, we should have int, string, and memory. So this thing should be the integer. Let's examine 1d from 0x40 2020 1, right? Then 21 38, and this should be the length of the string, so 5. And then if we increase by 8, we should see hello. So here we have 1, the pointer to the beginning of the string, so 5 and hello, and this is the actual hello pointer. Right, so then we call swap. So if we check again this thing, we should see nothing has really changed, but it looks a bit different. Oh no, yeah, I'm wrong. You can see that these things are in fact different. What? But I'm looking at the wrong thing. So this should be the same. Right, and if we go again with the next instruction and we check this place. You should see that. And now comes, so on the heap, right? Would be nice to see what's on the stack, but haven't really checked that well, so now it looks like shit. So we have this thing, which looks like complete zeros for some reason. We have 40, 30, and then nothing. So it's the first thing, which is 1 std out basically. We have 41, 30, 0, 8, which is the 5 for some reason. And we have 42, 30, 0, 0. I guess 42, 30, 0, 8, 41. Okay, what the fuck? Let's step into this one. So we next instruction. So now we are inside of the sys, right? So here we put a 1 on the stack, and then we do syscall 3. So let's get inside of it. And now we can go to main.sys so we can see the syscall stuff, right? So we do whatever, then we do stack pop. So in RAX we should see pointer to 1, right? So we get the 1, we store it, do another call, we should see the integer with the size, so we should see 5, right? Then we should see a pointer to hello, so we put that right into here, and then we do another call and we should see std out, which is 1, I think. So we fill in rx with the syscall, rdi with fd, rsi with the string, rdx with the size, and then syscall, and we get this error code. We get that error code. Interestingly enough, why did it? Oh, you know why it? Because I forgot to push the result of the syscall on the stack. That's why it's segmentation faulted. So I have to move. Actually, let's do it differently. Let's use integer push. Data int. So where is data int used? I need one good place. Oh shit. Oh yeah, here. So I need to do something like this. So here at the end, after the syscall, we need to do this stuff. All right, so we get some status 242. How do I figure out what error that is? 242. It's 255 minus 242, right? 13. But I mean, F volt, like, can I just say include unistd.h, and then can I just have a random a again and just go no. Linux syscall error codes. So it's one of these, probably, because I don't know if it's like permission. It cannot be, right? Out of memory doesn't make sense. Bad address, maybe it makes sense. Maybe bad address makes sense, right? Because yeah, well, we could have something like printf, and let's try to print it as unsigned, and we do 242, but I want it unsigned char. Really, do I have to put that? Wait, what? I mean, yeah, whatever, let's put it in. Like, what? Wait, I'm stupid. Should it be D then? Huh, how do I make it char? Yeah, minus 14. Oh my god, we are cooked because of this. We are actually cooked. But why is it bad address? Let's let's run this thing, and let's gdb again. So let's break start, run. Let's enter main, and I'm pretty sure. So it returned bad address, okay. But why though? Right. Why would it say bad address in this case? Is it like bad address because of the address of this hello string, or what? Isn't stdout number 1? Yeah, like it's stdout RDI. Okay, let's also check Linux syscall convention. Maybe I'm wrong with the convention. Oh my god, the register. Okay, perfect. It's here. Syscall number RDI, RSI, RDX. So I was decent. I mean, it was correct. But yeah, why is it saying bad address when RSI is just pointer to hello? Right, like if we examine string at this address, oh shit. Let's run it back. I need to see that before. So here we go to the syscall, and if we examine, why does it say I don't cannot access memory at because yeah, I mean the 64x at 04300. Oh, it's only one. Yeah, like the string is here, so why does it look so weird? Let's come again. Step instruction into that. So yeah, it stores that, then it takes 5, then and maybe I'm oh my god, that's the actual string value. Oh, that fucking sucks. So I'm actually dereferencing the pointer. Fuck. I'm actually dereferencing the pointer. And I have an idea. Right, so string memory is actually a pointer. It's like, fuck, how can we think about it? String memory is like char pointer, right? Or I guess int pointer. So when I come to this main thingy and I do the Linux syscall, I dereference that. Right, here I dereference it. I dereference that. And the reason why is this integer is actually a pointer to an int, but I guess here we have the pointer to like the first character. So if I dereference that, it sucks. So that's kind of bad. I mean, I would have to allocate. Like, let's think about it. So how would it make sense? String memory. Like, um, hmm. Mm-hmm. So I guess when I do string memory, where is that actually? I'm taking the address, right, and then push that address on the stack. I don't know where I want to do that though. So string memory. For me, it makes sense to keep it like this function, to keep it like string.memory gives you a pointer to the character. So it's a char pointer. Problem is for string length, for example, I allocate it. So then maybe it makes sense to also allocate this thing. So let's actually do that instead. Let's do it like that. So here, yeah, we take the address of this string. So what do I need to do is basically allocate some memory, like one word, and then store this thing in that place and then push the memory. So let's say we are gonna do that just to annoy people, hopefully. D0 is gonna be basically s.str. Let's say we store it so we don't think that much about it. So let's store it. Let's store it in D0. So next step would be to allocate memory. Interesting. So maybe what I'm gonna do is do rule 110 assembly, and let's see where I use allocate, memory allocate, right? So I need to do something like this. Allocate 1 and wait, do I have that? Yeah, I do. So I have to move 1 into this thing. Then we call stack push, although I wouldn't say stack push, I would say more, yeah, like writing everything into a single file is cool and all until you have to move between like thousands of lines. But I still don't regret doing that because it's more fun, to be honest. Like thinking about it, the reason why you would want to split your code into multiple files is like the editor being really slow, right? But yeah, so lu percentage s. So let's call to allocate stack func memory allocate null memory allocate. So yeah, we basically call to memory allocate. We allocate one word, so I could even say allocate one, kind of, right? We allocate one word. Then we stack push. I could say stack push. Or should I? Like, what happens after you memory allocate? And I don't like using memory allocate for this thing. I would rather just use allocate. Like if you think about it, memory allocate only does allocate, right? So what's the point? If I'm being honest with you. So I would say move RDI 8. So we allocate 8. We push that thing on the stack. But I also want first to store T0 in RAX. So emit. Should I do it like keyword RAX? And then I cannot do T0. I have to do something else, like RDI. And then emit move RDI keyword RBP minus log 0. That should do it. So yeah, here we store this thing, then we allocate 8, and there we put T0 where we allocated, right? So we allocate 8, we take T0 from the variable, we move it into the address of RAX, that, and then we push. So now allocate is gonna be basically stdlib. So allocate is basically memory char, if you think about it, right? It has this type, but for now it might work. So if I do 04 like this, we actually get hello, but it's also status 5. Because right, tells you how much it wrote, right? On success, how much it wrote. Holy shit, we actually have it. Right, so that was the fix. Because to make it more generic, to make our syscalling more generic, let's say, we have to assume that everything is a pointer here and we dereference everything, right? We cannot check if you have strings or booleans or something. We just dereference what you send, and then we call the syscall. So then if you put a string, the string is already dereferenced if you call to string memory. So we had to add an extra layer on top of it to wrap it into another allocate. So yeah, basically this, if we can use like generic arguments, it would be memory char, right? So it's a pointer to a pointer. Right. I mean, it is, right? Because here we allocate, and in T0 we have the address to the char. Yeah, so it's basically memory char. I mean, memory should actually be pointer, but yeah, whatever. I have to think about it. So we actually have syswrite function, sysread. This is gonna be really bad. Syscall read is actually the first syscall. It's int memory int. So it's 0 syscall 3. Right, read. The read syscall takes in the file descriptor, so it's gonna be 0 for std input, buffer, and how much do we want to read. Problem is we need to allocate the buffer. So how is string .read gonna work? I might think it's gonna be something like this. So you specify the oh, and as I said, string out, we can just implement it like this. So string out is gonna be basically 0 string dot write pop. And we no longer need this function because we can just call 0 string write pop, and that's that. Yeah, so read. How can we read into a string? So first let's dupe. Let's memory dot allocate. I would even say after dupe we have int memory, I would then swap. So we have int memory int. Problem is this memory is a pointer to an integer. So we'll see if we sys.read, and syscall.read is going to return an int. So it's going to tell us if everything worked. But that way we kind of lost our let's do something like this just to do something. 04. So what should I do? String read, and I said 1, and let's read like 5, and then I can do string out 0. So string write has, wait, string out, I put a 0. Oh, so I have to swap, and it's actually 1. Wait, no, string write, so we have string, yeah, it's fine. Okay, so now it complains about which function? String out. I have to run make. So obviously nothing happened. We don't even know if this thing worked, to be honest. Let's do int actually. And let's do that. So we see at least if we have echo status. Again, 242. So we have the same issue here with memory allocate, right? We dereference it. So we need to store it behind the pointer. Right, we need to store it, which kind of sucks. Right, because it sucks because and like it's a bit unintuitive, right? Like you see here, it's these are integers, so why? And then you see this as a pointer, so why do you have to have double pointer? Right, it's a bit unintuitive having to implement it like that. But we don't really have a choice, do we? Because integer needs to be dereferenced, it's just an address. But yeah, memory is actually, maybe it's memory that is not implemented properly. Maybe we wanted, when you do memory allocate, so the idea, right? Memory allocate allocates a pointer on the heap, or allocates a buffer on the heap, and it gives us the address to that, which makes sense, right? We allocate and it gives us the address to that. Or when we store something, we pop the memory, right? And we do all of that. But thinking about how our data types are implemented, kind of, right? The value is usually a pointer to the value. So for integers, we allocate, 8 bytes on the heap. We write the integer there, and then we take a pointer to that integer and we push it on the stack. For memory, we allocate a buffer. We take the pointer to the beginning of the buffer and we push that on the stack. If you think about it, it would be more stack-like if we allocate that, if we allocate a small, like 8 bytes on the heap to store the pointer in that location, and then push the address of that thing on the stack. So that's more stack-like looks more like our language. So I think we should try to do that instead. So yeah, here we allocate the buffer, but then I think we need to allocate once more, put the address of the buffer in that new location and then push the thing itself. So maybe it's like int push here instead of stack push, right? We consider the result of allocate to be an integer, so it's more stack-like. I think I'm gonna try that. So it's basically doing this thing. How does the int constructor look like? I'm curious. I just need to remember that, and then we can just try to achieve that. So int constructor allocates 8, puts 8 there, it allocates, moves it there, and then it puts the value and then it pushes the t0. So it's basically what we need, right? Doing push int, which is interesting. So let's actually try to do that. So what does that mean is string memory let's think about string memory. So string memory it has to do that. I don't know. Let's first handle memory, because that's gonna be more complicated. So here, right, I said that in RDI, where do I have some function calls that's important? Okay, so in memory allocate, instead of pushing the value directly, what I think I want to do is to call to basically int push, right? So instead of pushing the pointer to the buffer directly, we wrap it around an integer, which is just short for doing what string memory does here. So I guess we could do the same here. Instead of stack push, right, I can take the array x from here and do an int wrapper around the pointer to the string, right? So we have the pointer to the beginning of the string, or buffer is the same thing at this point. So we just make an int wrapper around it. I think this is more stack-like. So memory allocate. Then a memory store. We take the A, we take the offset, we get memory, but again, this is the int wrapper. So I have to dereference arrayx once. So it's the same as doing plus operation. So if we go to plus or multiplication, we do this extra dewrapping. I think it's gonna be more stack-like. I use this word a lot. So I think I'm gonna do this. So it's basically dereferencing the memory, and what I don't like about this though is here we push T2, but T2 is no longer the int wrapper. So what I'm gonna do is say T2 is gonna be the memory, but here we want to dereference array x once. So I think that's how we do memory store. Right, so that's how I think that's how you should do it. It's more stack-like. Okay, anyway, so how do we dereference something from memory? So we pop the offset. Here we pop the memory, so we have to dereference it again, right? We have to dereference it. Then we get the offset, we add the offset, and we stack push the result, which is something from the memory. So now I would say that if we go back to stdlib, this is actually now a memory chart. Oh, fuck. Shit. I mean, it's kind of memory char pointer, but it's so weird. It's, yeah. Oh, we don't have int yet. Well, int function is actually, yeah, I'm wrong about that. Int function is actually like this. I forgot that I made int function not available to the user. And the other place where we need it is in memory allocate. Right. So yeah, we just wrap it around an integer. So if we say hi, shit, we still get, no, we actually read it. Holy shit. We actually read that thing. Right, so it's gonna be interesting to figure out what the type of string memory is. But for reading, we actually managed to read something. So yeah. Question is, how are we gonna be able to save this memory? How are we gonna be able to save this memory? Because I don't know. So let's think about it. So I think I'm happy with memory allocate working like this. We just have to make sure that rule 110 still works. Phew, it still works, surprisingly. So yeah, basically I think that's how I want to have this thing. Right, we want to wrap it around another pointer. For both the string memory buffer and for memory buffers. So yeah. The new problem that we have right now is how are we gonna store this memory? How are we gonna store this memory? Because right now, you know, we swapped it. It's kind of impossible. Right, we have two integers. One of them is the file descriptor, one of them is the size that we want to read, and I kind of want to return a string. So here we duplicate the size so we can allocate a buffer, right? Memory allocate, so we get this result. Then if we swap, we get the thing from here. I mean, I really need the rot4. Because I would just duplicate and then rot4 prime, and that's it, right? Damn, this sucks that I need rot4. I was hoping to only need these. I mean, I could have tuple of two integers and just keep these two into a tuple. Right? So I would do what? After I allocate, I can just rot prime. So we do memory int I mean, I could even, oops, I could even do that here, I guess. So we have, I know that's too hard. Let's say it's gonna be fd nn. We have fd m, maybe doing like root prime and fd n, and then tuple nfd. So right, nfd, then we can dupe the memory, nfd m, then we can root prime, so we put memory back, then I can swap to do m. Well, I guess I can just root to bring this thing forward. Why not? Now I can dupe. Now I can dupe and this is gonna give us mm and fd and fd. I can say which one is gonna be the fastest. Doesn't really matter, it's the same thing. So I can do tuple fst, so we get mm and fd n swap mm a tuple snd, so we get now I would say root and swap. So maybe it was faster if I did snd and fst. So here it's fd actually, and here it's n. So this is fd. So if I do rotate, we are gonna have fd and m, then swap and fd and n, then I can do syscall, no, sysread, so it's m int, and maybe I can have a function swap int m string from memory or something. From memory. String from memory. But it's like, yeah, if the integer is less than 0, then it's an error. But let's assume that we, you know, handle error, maybe. Alright, so string from memory is going to be an external function. So it's int and memory, and we get a string. So it's basically the string builder. So I can say string int. right, is the way you initialize a string from int and memory buffer. Sounds kind of cool, honestly. Let's see. Main. So string init. Let's copy paste. So I said out is no longer gonna be a thing. String init. This shouldn't be that weird. How are we gonna do this one actually? Because I need to allocate. Let's think. So I need to pop. Let's do it like this. So we'll have t0 is gonna be the first item, so it's gonna be the length. All right, we have t0 is the length. That's what we need here. Int and memory. I guess let's call this one L for length. So t0 is gonna be the length. Right. We pop it. We actually take its value apparently. We take its value and we need to move it into some kind of variable. So let's find an example where we use a variable. So we store it into location 0. That's where we store the length value. And let's also take into t1, let's take the memory. All right, so we pop again, we dereference that thing. So this is gonna be now a pointer to the heap. So before it was pointer to memory, to that wrapper that we created earlier. If we dereference that, we get a pointer to the memory, to the heap. So we store that as well into t1. And now let's see how we build a string. How do we build a string? For example, string concat. We allocate, I guess, and we mem copy. So let me just copy all of this stuff. But I mean, we already have the memory allocated. Yeah, but it's not enough, right? It's not really enough. Because we need to allocate this much. Length plus 7. So let's take this one. Let's go to init. Let's put this one here. And let's say, okay, t2 is going to be t0 plus 7. So it's the length plus space for storing the length. Shift plus 8, right? So we take 0 and we store into t2. So now we have to allocate t2 into t3. We allocate, then t3 dot length is equal to t0. Right, we store that, and t3 dot length, this should actually be the memory, and rdx, what was rdx? The length, which is t0. So why do we call swap? We don't need swap. So what are we gonna do here is basically RDI is the first argument. It should be location 3 plus 8. RDX should be T0 and RSI should be T1. Am I right? Should be T1, but just T1. So like this. So we put T1 into RSI, and T1 is our memory. But I don't think we need keyword. I think we need Leia from there. No, I think it's move. Yeah, it's move. Sorry. Because we stored it in a variable. So we take that into RSI. Into RDI we put the destination, which is location 3 plus 8. And in RDX we put how much we want to copy, which is L. And then we call to memcopy. And then we have to push T3. And deallocate variables. We actually have how many variables? 4 variables, so we have 32 actually. 32. Usually I put more than I use just because sometimes I forget to update it, but I think we have only 4 variables, so that's how string init should work, I think. So let's check 04 and let's do string out 0. So this is gonna do an echo if it's gonna work. Shit. So allocate has non-matching arrows. Expected in but got tuple. Ah shit. So I duplicate. I rotate. Let's say I swap, so we get n. No, I should just rot like this. So it's NFD. We call tuple, so it's gonna be NFD, and then we swap. So we get NFD N. From memory, so it should actually be string init. Shit. I mean, I guess that's the idea of how you have to do it. I could just GDB just for the memes, break start. But so its segmentation folds into the read. Right, so this is the read. I guess, yeah. So it's like dup, rot, tuple, swap, memory allocate, dup, rot, whatever. This should be sysread, so we say hi. Then we have a swap. So if we examine 64, at x at 0x4333 1 is 0. I mean, it read, so that's obviously a good thing. I just wanted to see what we have on the stack for a second. So we have this thing and this thing. So if we examine 16x from 0x 40 30 10, some stuff. Interesting. And if we try to string in it, where does its segmentation falls? In the mem copy thingy, I guess. Yeah, I mean, that sucks. I'll try to figure that out on my own though, because yeah, unless it's something extremely obvious, but I don't think so. Maybe I mistyped something here in one of these places, but chances are small, to be honest with you, that I made something like this small mistake, I would say. Right, so yeah, I mean, I don't know for sure, but maybe that's what happened, right? So yeah. So this would be the function, and then after all of these, put the hi message, next instruction, and if we examine, I guess if I examine the stack, I kind of see that we have these two items. So the length and the memory. So here is the length. That's what I would say. There's a length. So 1D at 0x 40 30 10. It should say 56. That's not good, right? That doesn't look like the length. Maybe it's the other one. 40 30 00. No. Is it a string? 0x 40 30 00. Nope. 30 10. Nope. Oh, it should be like this. So the string is actually 413038. No, it's not. Okay, so I mean, yeah, again, I'm not sure. It looks like the stuff is not really what I expect on this heap, but I mean, the heap is not right anyways, so let me just, like, I would have to say 8x from here, and now this is the actual place of the length, and examine string at, no, examine 8x at 0x 40 30. I mean, I would say that the string is here. Examine string at 0x 41 30 40, but it's not, so I'm not sure. Right, so that's what I'm not sure about. So here at least Rx has the high, there it has the 3, which is the length, and now we get some weird stuff in here. Oh wait, did I put them the other way around? I don't think so. But yeah, I mean, I'll try to figure that on my own, because you know, we managed to get the read going, the write going at least, so probably it's like a mistake in my assembly here. So yeah, thank you for watching, and I mean, maybe I'll do an update at the end here with when I find a fix. So yeah, like, just for you will probably be 1 second, but hopefully it's not gonna be like 7 hours. So yeah, see you then. Okay, so funnily enough, I just found the error, and um, yeah, as I said, it was in the assembly. So I forgot that I was looking at these two types, and I was actually reading them in the reverse order in here. So I just swapped them around, and now we actually have hello world. I guess it only read 5, right? That's good. That's good, because in 04 type check we said read 5, right? So we only read 5 characters, which is hello, right? So right, so yeah, it only reads the 5 characters. We'll see how we can maybe make a nicer function that reads until, I don't know, like new line, but for now that's pretty decent. So std lib, string right, string out, right? So similar to how string out just prints a string, I'd like a function that just reads a string. Maybe you don't provide the size or something like that, so that would be like something like string in, right? But I think these are fine for now. So pretty decent language, I would say. We have Syscalls, so in like almost 2 weeks we were able to implement a programming language that has static types. It has access to Linux syscalls. What else? I mean, it's stack based, but that's not really huge. And how big it is, that's about, I'm curious. It's only, I mean, it's 3,500 lines of code, so 3,000, almost 4,000 lines of code basically. And yeah, I would really like to make it like self-hosted, so compile itself, because you know that's how, like, in stack-based languages that's the trend to what to do. But I think that's gonna be really hard because the language is so big, like the compiler is so big right now, and probably it's gonna take a lot of time. But the thing is that the more features we are gonna add, so if we add that generic type, it's gonna make it more difficult to port it to itself, right? So that's what I'm thinking. Like, are we there yet, or do we need this generic typing for memory? Not sure. I think, yeah, we can try to start, and if we see that we need some features, we can add them, right, along the way. But we have to keep in mind that when we add a feature, we have to also implement it in itself. So it's kind of a double-edged sword, right? It makes working with the language easier, but it makes writing the compiler harder. So that's funny how it works, right? The more complex you make a language, the easier it is to work with it, but it's also harder to write a compiler for it. So that's what we need to keep in mind. So yeah, but I'd say it's a pretty cool programming language. Like, it's kind of useful. I mean, I want to say useless because I mean it's useless, but it's fun to write code in it, right? I think that's important. And yeah, we have static types, we have type checking, we have syscalls. So yeah, like we can do anything kind of in this language, right? So that's the plan. Maybe next time we can actually start on some implementing the language in itself, and at some point we are gonna need an array of tokens, right? And that's gonna be the place where we need the generic memory. So yeah, but some other things that I've learned from doing this in a single file, like it's it's easier if you make it in a single file because you don't have to context switch that much. You can just use especially in Vim, you can just go from one file to the other really quick. So that's one advantage, I would say. The disadvantage is once you get to like 2000, it's a bit, I don't know if the right word to say is claustrophobic, because it's like, where the fuck am I? Right? So I'm not sure where I am in the code. But if I had a file for each feature, like one file for the assembler, one file for the type checker, and so on, it would be much easier, obviously. But I think this was the best approach, because the plan was from the beginning that I don't care about the C implementation that much. Even though I do care about it. That's why I did memory management, right, and try to make everything free, right? Even though, damn, 200 megabytes. That's so much memory. I'm not sure. Yeah, it's so much memory. Anyway, but yeah, like obviously I try to do as few allocs as possible. So that's worrisome. Like, imagine if I didn't try to do that, how big this would get. But yeah, I mean, I'd say it's a decent start. Obviously, there are more features that we can add to this language, but I'd say it would be nice to start on doing like self-hosting the language. I think that's gonna be interesting to try and do. But even if we fail, like if we fail, we fail. It is what it is. But let's try at least to start it, see how it goes. Then if we need features like generic types and something like that, we can add them in the C compiler, and then yeah, I mean, we'll deal with the extra stuff that we have to port. But I'd say that probably this is the right moment to try to get that going, because we have syscalls, we have syscalls, we have static types, so it's gonna be easier to not make mistakes. Yeah, sure, we have arrays. They are not done yet. They need the generics, but yeah, I mean, it's close, right? So it's close to being a complete language. So I mean, even if statements, we have if statements. We don't have for loops, which would be nice but not required. So yeah, and I guess that's everything for today. So we managed to add syscalls. We have type checking, so it type checks everything. We have a simple echo application, right? We can write into it and it spits out some text. So here we read, and then we output, return 0 to std out. or I guess to the return. And yeah, I mean, pretty cool language. So let's see in the next one. So see you.